Hello, today I'll present our work titled Singular Values-Driven Automated Filter Pruning. My presentation has three parts. First, I'll cover the motivations for network compression, including its advantages and challenges. Next, I'll review the taxonomy and background of network pruning and present our method, sliming. Finally, I'll share our experimental results and some demonstrations. Let's start with context. In recent years, deep neural networks have grown in both parameters and computational demands. In 2016, the largest model had fewer than 200 million parameters, but today, models can reach billions. For example, GPT-4 has around 2 trillion parameters and costs about $100 million to train. As these models grow, they become costly and complex. Model compression offers a solution. Model compression provides benefits like cost savings, reduced storage, lower computational demands, and on-device deployment. However, compressing models is challenging. We aim to reduce parameter count while preserving accuracy. This balance is tough due to information loss and the need for model-specific optimization. Several model compression techniques exist, including neural architecture search, quantization, pruning, low-rank approximations, weight sharing, compact module design, and knowledge distillation. Our work focuses on pruning, specifically using low-rank approximations. Pruning approaches can be classified based on 5 questions. First, what to prune, structured versus unstructured. Second, how to prune, by magnitude, similarity, etc. Third, when to prune, before, during, or after training. Fourth, how often to prune, one-shot or iterative. Fifth, how to set the pruning ratio, manual or automatic. Sliming is structured, one-shot, and after training, with an automatic pruning ratio based on multilinear singular values. Let's explore this further. To understand our method, let's review a few concepts. The singular value decomposition, SVD, factorizes a matrix into orthogonal and diagonal matrices. The nuclear norm of a matrix is the sum of its singular values. Tucker decomposition breaks a tensor into a set of matrices and one small core tensor. Higher-order SVD is a specific orthogonal Tucker decomposition, generalizing matrix SVD. We use the multilinear singular values to capture variation in a specific mode, formulating our pruning problem to retain interdependencies. We define the nuclear norm of a tensor as the nuclear norm of its mode 1 unfolding matrix. Now, let's reformulate the problem. Given a predefined number of filters to retain across all layers in a CNN, we need to determine 1. How many filters should be retained in each layer to maximize accuracy? 2. Which filters to retain in each layer for optimal accuracy? For example, in a simple CNN with 3 layers and 15 filters, we'd remove 1/3 of them as shown in the figure. We formalize this with equation 1, aiming to identify how many and which filters to remove. Due to the problem's combinatorial nature and large search space, we simplify it into 2 subproblems. First, we determine the optimal number of filters per layer that maximizes the sum of nuclear norms across all layers. Once set, we solve the second subproblem by independently selecting filters for each layer that maximize the nuclear norm under this constraint. We introduce 2 straightforward algorithms for these tasks. Our method identifies the optimal filter configuration across layers within a constraint on total filters. The core idea is to select the largest singular values iteratively from all layers until reaching the target filter count. The algorithm picks the largest singular value in each iteration, increasing the retained filter count for the layer. This continues until the desired filter count is met. Here's an example of the pruning configuration estimation algorithm. In a CNN with a target of 10 filters, the goal is to keep 3, 3, and 4 filters in each layer. The algorithm iteratively selects the largest singular values from all layers, incrementing the retained filter count for each layer. This process continues until reaching the target filter count. We introduce GEM, an algorithm for solving the second optimization problem. This stage assumes the optimal number of filters to retain per layer is already set. GEM aims to identify, for each layer, the set K that maximizes filter independence. This preserves the network's core functionality by retaining filters that collectively enhance predictive capacity without redundancy. An exhaustive search is impractical for deep CNNs due to the vast search space. We use a heuristic strategy that removes filters until only the most significant ones, based on our objective function, remain. This method removes filters that cause minimal or no reduction in nuclear norm, indicating redundancy. We evaluated our method on 5 architectures: VGG, GoogleNet, ResNet, DenseNet, and MobileNet v2, tested on Safar 10 and Safar 100. To assess sliming scalability, we also tested on ImageNet using ResNet 50 and MobileNet v2. Additionally, we used compressed ResNet 50 as the backbone for faster RCNN-FPN, Mask RCNN, and Keypoint RCNN on the COCO 2017 dataset, comparing sliming against 56 related works. The next slide shows the pruning results for VGG 16BN on Safar 10. To further test scalability, we evaluated sliming on the ImageNet dataset using ResNet 50. Across all compression levels, our method consistently outperformed others in both performance and complexity reduction. Here are the results for faster RCNN on the COCO 2017 dataset. Sliming significantly boosts inference throughput, achieving over double the frames per second compared to baseline models. Next, we show results for human keypoint detection. All performance evaluations were conducted on a GTX 3060 GPU, demonstrating sliming's real-world applicability. These results highlight sliming's potential for enhancing neural network efficiency in demanding tasks like object detection, instance segmentation, and keypoint detection. This work used high-performance computing resources provided by the Grand Équipement National de Calcul Intensif. We are also supported by the Agence Nationale de la Recherche. The code is available on the project homepage. Give it a try. Thank you for listening.